Hello, my name is Dr. Michal Scanlon, and today I will present recent research in my group to develop a soft on-off switch based on the electrochemically reversible HJ interconversion of a porphyrin membrane at an electrified liquid-liquid interface. So this work is carried out by my group in the Department of Chemical Sciences at the University of Limerick, and also in collaboration with Professor Nagatani and his group at Kanazawa University in Japan. So I'll begin with an outline of my presentation. So in this presentation, first of all, I will explore the precise experimental conditions to self-assemble a zinc porphyrin membrane consisting of interfacial nanostructures at an immiscible liquid-liquid interface. So then I will show how ions can be dynamically moved in and out of the porphyrin membrane under electrochemical control at the interface between two immiscible electrolyte solutions. This is known as the ITIs. Then I will discuss the underlying mechanism underpinning the electrochemical response of the porphyrin membrane at ITIs, and finally show that reversible HJ interconversion of the interfacial nanostructures within the zinc porphyrin membrane is possible by varying the applied galvanic potential across the ITIs. So in other words, we're going to electrify the liquid-liquid interface. The structure of the porphyrin membrane will change in response to that electrification or change in potential at the interface, and that will be reversible. And this reversibility will allow us to create on-off switches based on this feature of the porphyrin membrane at the liquid-liquid interface. Okay, so let's begin to discuss the self-assembly of the porphyrin membrane at the interface. So we described this process in detail in a recent article in Journal of Physical Chemistry C. So the aqueous phase consists of the porphyrin solution, and the organic phase is simply neat organic solvent. So in this case, trifluorotoluene. Absorption of the porphyrin membrane occurs within a few minutes at the liquid-liquid interface, as seen by a yellow coloration of the interface. Now, remarkably, the bulk aqueous phase containing the porphyrin can be easily replaced by serial dilution with a blank buffer solution, and this leaves us with just the porphyrin membrane stably formed at the interface between an aqueous buffer solution and a neat organic solvent. So we transfer the film off the interface onto silicon chips, and we carried out scanning electrochemical microscopy to reveal that the membrane was about 150 nanometers in thickness and quite uniform in its features. X-ray diffraction clearly shows that the interfacial porphyrin contains macroscale domains of long-range order. And this is because the liquid-liquid interface is defect-free, and it allows ensembles to be formed with high structural perfection. So that means they can show crystallinity. This is a big advantage of the liquid-liquid interface over self-assembling materials, for example, at solid-liquid interfaces or just in bulk aqueous or organic solutions. Key feature or key variable is the pH of the aqueous phase. The pH of the aqueous phase must be set to match the pKa of the carboxyphenyl group on the porphyrin molecule that we're using. Now at the pKa, statistically half of the porphyrin molecules in the aqueous phase are anionic here and deprotonated, and the other half are fully protonated and they're neutral. Now, molecular dynamics simulations were carried out by Professor David Chung at the National University of Galway in Ireland, and he showed that the porphyrin molecule that is protonated adsorbs directly on the liquid-liquid interface, whereas the deprotonated form of the porphyrin, which is more hydrophilic, will reside 5 angstroms away from the aqueous phase in the aqueous side of the interface. This makes sense. So therefore, we propose that the porphyrin membrane is formed using a layer-by-layer strategy. The hydrophobic porphyrin forms the base layer onto which the anionic porphyrin can adsorb by non-covalent interactions. And these would be things like pi-pi interactions or hydrogen bonding. Now, this means that if we replace the aqueous phase by a more alkali solution, such as at pH 7, 8, or 9, then the hydrogen bond network will break down and our porphyrin film will dissolve. However, once formed at a pH of 5.8, the aqueous solution can be adjusted to more acidic conditions while maintaining the porphyrin film at the interface. So in other words, the hydrogen bond network will remain stable at acidic conditions, allowing the porphyrin membrane to maintain itself at more acidic conditions. Now, certain liquid-liquid interfaces are formed between water and trifluorotoluene or water and 1-dichloroethane, and these are electrifiable. Now, a special 4-electrode electrochemical cell has been developed to electrify the liquid-liquid interface, and effectively the working electrode is the liquid-liquid interface itself. Now, this cell also contains a reference electrode in each phase of silver and a platinum electrode in each phase as the counter electrodes. Now, unlike at solid electrode-electrolyte interfaces, where electron transfer is primarily studied, at DTs, both ion transfer and electron transfer can be studied either simultaneously or individually. Now, importantly, all electrochemical techniques used at solid electrodes, such as cyclic voltammetry, can also be applied at DTs. However, the meaning of the CVs is different. For example, the width of the polarizable potential window at the liquid-liquid interface is determined by the ion transfer potential of the electrolyte cations and anions in the aqueous and the organic phase. Now, the organic electrolyte we use in our experiments is here. It's this very hydrophobic molecule, and I show it because the organic cation is going to interact a lot with the porphyrin membrane and be responsible for the electrochemical signals that we're going to see now in these upcoming slides. Okay, so the electrochemistry of the zinc porphyrin film was probed using the 4-electrode cell. So here you can see the porphyrin membrane separating the aqueous and the organic phase, so floating nicely at the interface. In the aqueous phase, we just have lithium citrate salt at pH of 5.8, and in the organic phase, we just have the hydrophobic electrolyte salt. So we do two experiments, one CV in the absence of the porphyrin film, and one CV in the presence of the porphyrin film. In the absence of the film, we essentially get a featureless CV. However, in the presence of the film, we get several signals at negative potentials. So we call them A, B, and A'. Now, there are no redox active species in either the aqueous or the organic phase, and this means that the signals due to the porphyrin film are purely ionic in nature. Okay, so let's look at these electrochemical signals in more detail. So we switch the potential just after peak A' has formed. And we get a different peak now on the forward sweep. We get this B' peak, which is much smaller, and it's a near identical shape to A'. Therefore, the electrochemical process giving rise to the peak A' was the reverse of the electrochemical process giving rise to the peak B'. We then carried out scan rate studies, and these revealed several features. So first of all, we found that the charge of the magnitude of the charge under A' and B' was identical from scan rates of 1 up to 25 millivolts per second. Also, the peak-to-peak separation of these films was tiny. It was only 5.9 millivolts at a scan rate of 1 millivolt per second. And also, the peak current increases linearly with the scan rate. So the conclusion from these experiments is that the electrochemical signals observed in the presence of the zinc porphyrin membrane were due to a diffusion-less process. So either adsorption or capacitive phenomenon and not Faradaic ion transfer. So this is a key insight into the electrochemical mechanism. Now, the electrochemical signals were also due to processes involving carboxyl groups within the zinc porphyrin membrane and not only at surface sites facing the aqueous and the organic electrolyte solutions. So to prove this, we did an experiment where we increased the concentration of the porphyrin in the bulk aqueous phase, and we formed various porphyrin films with increasing surface coverages. And what we see is a linear increase in the peak charge was obtained despite the interfacial surface coverage far exceeding that expected for a monolayer of porphyrin at interface, which we estimate at 0.095 nanomoles per centimeters to the -2. A clear conclusion is that the electrochemical signals are due to carboxyl groups both within the zinc porphyrin membrane, not only those that occur and face the aqueous or the organic electrolyte solutions. So within a certain potential range, the zinc porphyrin membrane is therefore acting as an intermediate phase separating both the aqueous and the organic electrolyte solutions. So we show this here in the schematic. Here we have the zinc porphyrin membrane separating the aqueous phase from the organic phase. In the organic phase, you have the organic electrolyte, and the aqueous phase, you have the aqueous electrolyte. So when the galvanic potential is scanned progressively more negative, the organic cations are pushed into the film, but they cannot transfer to the aqueous phase. Instead, a few protonated carboxyl groups are forced to dissociate. And many more of them transform into this species here, which is a carboxyl group associated with the organic cations. In both cases, protons are released, and these protons transferred or pulled into the aqueous phase. Now, the charge of the anion carboxyl groups remaining can be compensated by other organic cations present in the film. Conversely, when we switch potential to less negative potentials, you get the opposite. So now protons enter the film and the organic cation exits the film into the organic phase. And this is the process giving rise to our electrochemical signals, and it's actually capacitive in nature. So when we scan negatively, we get a buildup of positive charge here at the organic side of the interface and negative charge due to the loss of protons on the aqueous side of the interface. Now, the peaks of the CV we get are very characteristic in our system. They're very narrow. And these narrow absorption peaks are considered to be indicative of positive cooperativity. So what is positive cooperativity in this case? So once the initial bulky organic cations flow across the oil membrane interface as the potential is scanned negatively, it will open space in the nanostructure due to a structural rearrangement of the porphyrins within the membrane. And this structural rearrangement allows later organic cations that approach to penetrate into the membrane much more easily. And this is known as positive cooperativity. Less energy is required to penetrate the interface with the organic cations that come after the initial organic cations in effect. Now, the CVs that we get at the liquid-liquid interface in the presence of the porphyrin film are near identical to those seen at solid electrode interfaces for processes involving phase transitions. So, for example, electrochemically driven structural changes of copper add layers on gold 111 electrode surfaces. So here is our electrochemical response in the presence of the porphyrin film, and here is the electrochemical response for copper UPD on gold in sulfuric acid and copper sulfate. So you can see that this response here is identical to our response at the liquid-liquid interface. So here you have a structural rearrangement of the porphyrins, and here you have effectively a phase transition or structural rearrangement of copper add layer on gold. So why are the electrochemical signals the same, even though one is at a solid electrode and one is at a liquid-liquid interface? So the reason is that both of the thermodynamics for both of these systems can be analyzed using the Frumkin isotherm. So that's what's in common between both. So we in collaboration with Professor Jose Manizares from the University of Valencia, we simulated the shape of our CVs precisely by incorporating Frumkin isotherm into our equations, and that's described here in our other Journal of Physical Chemistry C paper from last year. Now, to probe the structural rearrangement of the porphyrin membrane, we developed a UV-vis technique in total reflection mode at a liquid-liquid interface. So light from the lamp is focused on the interface at an angle greater than the critical angle at the water trifluorotoluene interface, so that's about 80 degrees, and that allows it to undergo total internal reflection and be collected using an optical fiber where it's returned to the spectrometer. So when the applied potential at the interface is applied, you get a H to J interconversion seen in the porphyrin membrane, and that can be detected by UV-vis spectroscopy. Okay, so here the next step in our experiment is to create differential spectra. And these are obtained by subtracting the spectrum of the porphyrin membrane obtained at a positive potential of 0.5 volts from the porphyrin from the spectra obtained at different potentials. Now, a potential is negative of the potential of zero charge, which we calculated as 0.25 volts. Here, you get a buildup of organic cations at the organic electrolyte membrane interface. And this causes partial opening of the nanostructures, leading to the appearance of a J-type structure. So how do we know that? So here you have the potential being progressively scanned negatively, and they're differential spectra. So each of these spectra is subtracted from the spectra at plus 0.5 volts. So you can see it's flat there for 0.5 volts. And as we scan negatively, we see the appearance of a J-type nanostructure and the disappearance of the H-type nanostructure at the liquid-liquid interface. So this is the structural change of the porphyrin membrane at the liquid-liquid interface, clearly detected spectroelectrochemically using differential total internal reflection at the liquid-liquid interface as the unique, quite original technique. Now, this process is incredibly reversible. So here you have the scan where the potential is stepped from plus 0.5 volts to minus 0.3 volts and back again. And you see that the signal is beautifully reversible. Now, in fact, the signal can be cycled many, many times. So we just did it here at 30 cycles, and it's excellent reproducibility, highly robust. And this is, and the optical, so the reverse, our system shows a highly reversible response in terms of the optical properties of the porphyrin membrane. So here it's working as an on-off switch based on it undergoing structural interconversion from H to J type nanostructures as we vary the galvanic potential. So to look at this further with Professor Negatani, we looked at in situ polarization, modulation, fluorescence of the porphyrin membrane using the setup that he's reported several times in his papers over the last 20 years. Now, these PM-TIRF signals are a function of the emission wavelength, and they're recorded at different potentials. So the beauty of this technique is that it's interface specific. So the fluorescence is only emitted or detected for signals for species that are absorbed at a liquid-liquid interface, and signals from randomly orientated molecules in the bulk aqueous or organic phase cancel each other out. So you only get a fluorescent signal from a molecule that is effectively templated at the interface and is not randomly orientated in bulk solution. So the molecules in our porphyrin membranes should therefore give fluorescence output, and they do. So here we have two peaks seen at positive potentials, and they're negative in magnitude. And the fact that they're negative in magnitude means that they must have a relatively horizontal orientation relative to the plane of the interface. So then when we go to more negative potentials, we see a major decrease in the fluorescence, but no shift in the lambda max, so no spectral shift. Now, the decrease in the fluorescence may be associated with a change in the molecular orientation of the molecules within the membrane at these negative potentials, and the lack of a spectral shift has been associated with the fact that the porphyrin molecules in the membrane are mainly interacting with each other through hydrogen bonds in their carboxyl groups. So that fits well with our theory. Now, when you apply a very negative potential of minus 0.3 volts, the spectra does shift, it red shifts, and you get the appearance of this new peak at 694 nanometers. And this is attributed to close pi-pi stacking between porphyrin molecules in the membrane and during the formation of J-type nanostructures. Okay, so here we see J-type nanostructures formed at very negative potentials and a different spectra at negative potentials versus at more positive potentials. So that's quite reminiscent of what we see at UV-Vis experiments. So therefore we cycle between positive and negative potentials, and we see the peak here due to the pi-pi interactions associated with the J-type nanostructures appearing and disappearing reversibly with cycles. So this again is another proof that we have an interconversion of the structure of our porphyrin membrane as we apply a potential at the liquid-liquid interface. So it's acting as an on-off switch. So the conclusions from my talk today: a potential difference between two immiscible electrolyte solutions, so the ITIs, allows the intercalation of the organic cation from the organic electrolyte into the membrane, and protons in the porphyrin membrane will be exchanged with that organic cation. Insitu UV-Vis spectroscopy shows that the ionic intercalation and exchange induces a structural interconversion of the porphyrin molecules within the membrane. They move from a H-type nanostructure at positive potentials to a J-type nanostructure at negative potentials applied at the liquid-liquid interface. And these structural interconversions are reversible over 30 cycles, and this opens up now opportunities for us to use this membrane at the liquid-liquid interface as an on-off switch. In situ polarization, modulation, fluorescence spectroscopy further provided evidence of structural interconversion of the porphyrin membrane as the organic electrolyte cations intercalate, and they affected the emissive properties of the porphyrin membrane. So we saw the appearance of that extra peak at 694 nanometers, only at negative potentials. I'd like to acknowledge my group, especially Dr. Andreas Melina, who's now in Sweden as a postdoc, and my current PhD student, Ivan Robeo Melina. I'd also like to thank Professor Negatani and his outstanding student, Dr. Sho Yamamoto, who visited us in Ireland a couple of years ago. I'd like to thank my funding agencies. And also, finally, I'd like to thank you for your attention. Thank you very much.